Okay, so now we will talk about the method of characteristics and how to solve PDEs, certain PDEs using this. So we'll talk first about level curves, gradients, and dot products, and then talk about the transport equation using the method of characteristics, and then summarize that. So level curves, gradients, and dot products, some vector calculus stuff. Given a function of two variables, a level curve is, now where did I put my, and there it is. A level curve is where we set the function equal to a constant, we try and solve for that. Level curves are generally smooth enough that they have tangent vectors v. The gradient of the function is grad u equals ux ut. Sometimes I'll write them in bold, sometimes I'll not, because a little bit of a pain. Sometimes I'll write vectors in bold and sometimes I will not, because it's a little bit of pain of turning everything into bold when you're typing these things up. But gradients are generally orthogonal to level curves, which means that grad u dot v equals 0. So if v is a tangent vector to a level curve, then that's going to be orthogonal to the gradient. So here's a function u of x comma t equals x squared minus t squared. Sketch some level curves, add some tangent and gradient vectors. What's the gradient? And which level curves are not like the others? So to calculate level curves, what we need is some constants, right? So if c equals 1, then the level curve, LC, is x squared minus t squared equals 1. We just take our function and set it equal to 1. And what does that curve look like? It's a hyperbola. But if you look at this equation, you can see that x can never be equal to 0, right? Because if x was 0, then minus t squared equals 1, and we actually want to be in the in the real plane. So x can never be equal to 0. T can be equal to 0, though. If t is equal to 0, x is equal to plus or minus 1. So we know that it's a curve that goes through here. And the difference always being equal to 1 actually turns this into a hyperbola, which I'm not expecting you to know off the top of your head, but you can certainly get maple or GeoGebra or some other function to tell you what that is. So c equals 1. C equals 2 would be x squared minus t squared equals 2, right? And now if we set t equal to 0, that makes x plus or minus square root of 2, right? So that would be here and here, and then we'd still have the same shape of a hyperbola. Note that the hyperbolas are closer as they get out than they are in the middle. What about c equals minus 2? Well, you plot x squared minus t squared equals minus 2. And note here that if t is equal to 0, then x squared has to be negative, which we can't have. So t can never be 0. So that means we'll never actually cross the x-axis, but we can have x equal to 0. And if x is equal to 0, then t has to be plus or minus square root of 2. And so we get this. It's got a little too close there. So this is c equals minus 2. This one is also c equals minus 2. This is c equals 2 here. Going up this way. Nope. This one is c equals 2. This one is also c equals 2. If we had c equals minus 1, that would look like this. And c equals minus 1 would squeak through there. Finally, so minus 1 would give me x squared minus t squared equals minus 1. Finally, the 0. X squared minus t squared equals 0. That, if you solve it, becomes x squared equals t squared, or x equals plus or minus t. Those are the asymptotes of all these hyperbolas, although this is a really terrible drawing. And they're just these straight lines. Right, so this x running through the middle here, that's the c equals 0. Great, so those are the level curves that are not like the others, right? And it's this one. And there's something special about them because what's the gradient of the function? U equals x squared minus t squared. So grad U is 2x minus 2t at x equals 0, t equals 0. At the origin, grad U equals 0, right? That's our critical point. So the level curves that go through the critical point tend to be different from level curves that go through other points. The gradient of the function is perpendicular to the normal curve. So there's our gradient. We actually plot these vectors, and it points in the direction of increasing c. So c equals -2, c equals -1, c equals 0, c equals 1, c equals 2. All my gradients point this way. And here they point this way. Right? So the level curves, if you think about the level curves will have had tangent vectors that are perpendicular to my gradient curves, or my gradient vectors. So x squared minus t squared, that's what the level curves look like, and that's what happens at the origin. Okay, so using the method of characteristics. So first order linear PDEs, like the transport equation, can be solved using a method of characteristics. So how does that work? Well, suppose we have ut plus 7ux equals 0. So we'll note that grad u equals, well, I'm going to write it, I think I've been writing it ux and then ut. Yeah, so I'm writing it ux ut. So I'll leave it as ux ut. So this equation is ux comma ut dot 7 comma 1 equals 0. So that's interesting. Gradient of u is dot the vector 7, 1 equals 0. So what does that tell me about this? Well, gradient of u is perpendicular to tangent vectors of level curves. But it's also perpendicular to the vector 7, 1. So what can we say? Well, that's a tangent vector. So can we figure out, if we know what the tangent vectors are, can we figure out what the level curves are? And that question becomes a system of two ordinary differential equations and two unknowns. Why is that? Well, imagine that I have, how am I doing my notation? X is the horizontal and T is the vertical. Suppose I have X and T, and I've got vectors that are 7 in the X direction and 1 in the T direction. Oops. Oh, well, I can undo that. So 7, 1, so that's like this. So we just have a field of these vectors. So what are the vectors, what are the curves that are tangent to that? Well, those are these straight lines, although I'm not drawing them very well. So we've got a constant vector. What are the curves that are parallel to a constant vector? Those are straight lines. So I need a new parameter. We'll call it S. So for these curves, right, which are parameterized by S, what do we know? We know that dx ds has to be 7, right? Because that's the vector component in the x direction. And we know dt ds has to be 1 because that's the vector component in the t direction. What does it tell me? X is 7s plus a constant, call it C1. T is s plus a constant, we'll call it C2. So this tells me that s is t minus a constant. Plug that back in. X equals 7t minus 7c2 plus c1, or at the end of the road, x minus 7t equals a constant. Which isn't surprising. We expected these lines, these solutions to be lines. We got lines equals to a constant. So that works out just fine. So how do we use this to solve our equation? Well, remember that 7, 1, it's a tangent vector to a level curve. What does that make this thing? Well, these things those things have to be level curves of u of x comma t, right? So if we take f to be any function of one variable, well, not any function, right? We want it to be differentiable. Then u of x comma t can be equal to f of x minus 7t. This is our constant, right? For our level curves. So these are the level curves. So any function of the level curves will actually be a solution to this. Why do we know that? Well, ut plus 7ux equals 0. Okay, ut plus 7ux is the equation. So left-hand side is ut plus 7ux. Now, what's ut equal to? Well, that's going to be the derivative with respect to t of this function. And so we're going to have a chain rule going on here because we have a nested function, plus 7 times the derivative with respect to x of f of x minus 7t. So what's our chain rule look like here? Well, f is just some function. So we differentiate f, and it's a function of one variable. So it doesn't have partial derivatives. It just has its own derivative, which we call f prime, of x minus 7t, derivative of the outside, times the derivative of the inside with respect to t. So this times minus 7. What's the derivative of, well, 7 times d by dx of this? Well, the partial derivative of this, derivative of the outside of f, that's just going to be f prime of the inside, times the derivative of the inside with respect to x, which is just 1. And that equals 0. Yay. So one thing that happens in differential equation, in partial differential equations that you don't really see in ordinary differential equations, instead of having plus a constant, we often end up with an arbitrary function, right? Any function of x minus 7t, right? If this is equal to a constant, you get a function that has x minus 7t as its level curves, right? So if x minus 7t is equal to 5, then f of 5 is the constant, and that can be our function of u that we're looking for. Okay, so how do we fit this with Maple? Well, we found that the solution to this is a function, any function of x minus 7t. But we want u of x comma 0 to be equal to e to the minus x squared. So the exp here, that stands for exponential, which stands for the e raised to that power. And so we want that to be equal to f of x. This is our function of one variable that we chose. So what is f of x? We're now evaluating this constant. F of x equals e to the minus x squared. So what's a function that solves this equation and matches this initial condition? U of x comma t must be e to the minus x minus 7t quantity squared. Because how do we get our solution? We take this function, f of x, that's our function of any variable, and then we plug x minus 7t in for the x. So there's our x minus 7t squared. Okay, so interesting, but let's see if we can actually capture that on Maple. So I'm going to switch the share. I don't know if people have seen Maple or used it before. It's a useful way to visualize things. So we'll take a little look at it. Hopefully you're seeing this blank screen that has Maple on it, and we want to be able to graph some stuff. So we'll type in first with plots. So plots is a library, right? And it's got a bunch of different commands in it, some of which we want to use. So how do we define a function in Maple? You give it a name, which is f, and then we're defining it. And so the command for defining is command equals. So the command for defining something is colon equals. So f colon equals tells Maple that I'm defining f as something. And I want it to be a function. What do functions do? They take inputs, x comma y. And I'm using y instead of t here. Goes to, maps to, and the function we're interested in is exp of minus y minus 7x quantity squared. And so there's our function, and it knows, right? If you ask it, what is f of 0, 1, it'll tell you it's e to the minus 1. Great. So we want to plot this, but it's a function of two variables. So we need the plot 3D command, 3D, and that plots functions in 3 dimensions. And what you have to do there is you have to tell it that I want to plot my function f of x comma y. And I need to tell it what ranges on x and y I want. So suppose we set x equal to -2 ... 2, and that tells it the interval from -2 to 2. Its formatting is -2 ... 2, and we want y equals -2 ... 2. And then hopefully when we hit enter, it should give us a map. And there's our map. The x-axis is here. The y-axis is here, and then this is the output axis. And it's not great because there's these lumps at the top. You can scroll it around. And the lumps aren't particularly good. We don't like that. But that's an artifact of the programming. It's just not using enough points. So num points stands for number of points. And if we make that much bigger, say 100,000, which means just use a finer mesh to calculate this thing, it gives us a much better picture. And again, x is this way, y is this way. Think of y as time, right? And so over time, right, time is going up this way. This is what the distribution looks. So at a particular time, right, my distribution is at a particular place and it goes upwards. You can see that along each line, well, it's hard to see and it's a little hard to get this thing to move around. But there's these lines that have slope 1/7, or slope 7 actually. And along every line of slope 7, this thing has the same height, right? So it's level curves of these lines of height 7, right? And here's the level curve c equals 1 right at the top, right? And these are level curves that are very small because the exponential drives it down to 0 pretty quickly. So that's one way to visualize what your solution looks like. Again, though, a lot of these things are meant to represent physical physical things. So instead of having t as an axis, we'd like to have t as a parameter. And so you can, and this is a really bizarre formula. So plots, open square bracket, animate. And then what is the thing that I want to animate? I want to animate, well, I have to tell it that I want to animate a plot. And I want to plot f of x comma y, f of x comma t, for x equals, say, minus 20 dot dot 20, and it should be a square bracket, comma t equals minus 5 dot dot 5. So let's see if this actually works, and I should close that parentheses. Oh, and now it's screwed up. So let's hang on a second and let me fix this. Okay, so I figured out what the issue was, and the issue was that you have to put the animate here inside of these square brackets. So it's plots, square brackets, enclosing animate, and then open parentheses, plot, square brackets, the function you want to plot and arrange on x, and tell it what you want as the parameter, which is t, and then t equals minus 5 to 5. And then you get this, which is kind of a weird looking thing. So, but what you can do with it is say, animate it and play. And maybe I got my numbers backwards. Let's do this from minus 5 to 5, and this from minus 20 to 20. Okay, that might be better. Animate. There it goes. And we can put it on a loop, I think. There it goes. So what's going on here is I've started with some kind of initial distribution of this stuff, right? And I'm thinking of this as some stuff moving down a river or something. And we haven't included any diffusion terms or dispersion terms, right? We're just transporting it. We're just moving it down the river. And so this is the concentration of this stuff as time increases from minus 20 to 20. There it goes down the river. And this animation and this picture are exactly the same thing. What this animation is doing is going, you know, as y increases, going this way, right? The x is shifting over to the right. So it does actually model transport reasonably well, right? There's a thing that's moving downstream, but it's can be made much more complicated by including diffusion things. Like if you have a chunk of pollution dumped into a river, you want to know not just how fast is it going downstream and dealing with whatever's in the river, but also how fast is it diffusing away from its initial condition. And so that can be done in a lot of other ways. So I will go back to my lecture notes. I hope, there we go. So there's the illustration with maple, right? It really is this shape. This shape, which is like this, well, that's a bad drawing of it, at t equals 0, and then at t equals 1, it's moved to the right a little bit, and at t equals 2, it's moved to the right a little bit more. So you state your initial shape, and then the transport equation transports it downstream at, you know, speed of 7 units per whatever. So what's the summary of the method of characteristics? If we have this equation, right, this is the same thing as saying f of t comma x comma g comma x as a vector dot grad equals 0. So this vector is a tangent vector to the level curves of uxt, which means that the level curves of uxt are this solutions to this system of differential equations. And S is some parameter that just is measuring arc length along your level curves. So if you eliminate the parameter S, right, dx ds over dt ds equals dx dt, and that's this divided by that. G comma x. And so that's a differential equation that you should be able to solve. Right? And once you get that, then you have a general solution, and if you figure out what the initial condition gives you. So x of ut plus t ux. So f of t comma x is the coefficient of u sub t, time derivative. G of t comma x is the derivative of u sub x. And we want the derivative of g of tx of u sub x divided by the derivative of u sub t. So we want dx dt to be equal to t over x. So what's that? We can separate our variables, get x dx equals t dt, gives me x squared over 2 plus t equals t squared. Oop, I left out a step. Sorry about that. So separate the variables by multiplying, getting all your x's on one side, all your t's on the other side. So we multiply both sides by dt and by x. And then we can integrate both these sides. And once we integrate that, we get 1/2 x squared equals 1/2 t squared plus c, or x squared minus t squared equals some constant, right? And this is the very first thing that example that we looked at. I guess technically 2c. So any function the function of one variable, then f of x squared minus t squared is 1 over u x comma t, is one of our solutions, right? And so if we want u of x comma 0 equal to arctangent of x squared, that's our initial condition. From this, we get u of x comma 0 by plugging t equals 0, gives me f of x squared. So comparing these two things, that's telling me that the function I want for this is arctangent of x. So what's my solution to x ut equals? So we have x ut plus t ux equals 0. U of x comma 0 equals arctangent of x squared, as solution u of x comma t equals arctangent. We take our x and we replace it with our level curves, x squared minus t squared. Great. So how do you check this is true? U sub x is the derivative of arctangent of x squared minus t squared. Remember that derivative of arctangent is 1 over 1 plus x squared. So this becomes 1 over 1 plus x squared minus t squared, right? Because that's the thing inside the arctangent squared, times the derivative thing inside with respect to 2x. Ut, the derivative of this with respect to t is going to be, using the chain rule again and thinking of x as a constant, 1 over 1 plus x squared minus t squared squared, because that's the derivative of arctangent. I suppose I should write that out here on the side. The derivative of arctangent of x equals 1 over 1 plus x squared. So using the chain rule again, times minus 2t. So tux equals 2xt over 1 plus x squared minus t squared, quantity squared. Xut is minus 2xt over 1 plus x squared minus t squared, quantity squared. If you add those up, you get 0, which is what we want, right? And so you can see how the differentiation of the arctangent just gave you something that, was the same in both, so we didn't have to worry about it much. So that's the method of characteristics.